Okay. Uh, so the kind of basic idea behind both of these is it's all about osmotic pressure. Okay. So when you start thinking about the way the looseness of our stool works, it's all about how much water is in the stool, right? And that's all about osmotic pressure in the GI tract. And so when we think about diarrhea, we're thinking about things that lead to too much solute in the GI tract, right? If there's too much solute in the GI tract, that pulls fluid into the GI tract and makes it for too much water, makes it too loose, makes it move through too rapidly, right? So different things that can do that can be infections of our intestines, right? So when those cells along the lining of our intestines are inflamed and have an infection, then they don't do their job properly, right? They can't release the right enzymes for digestion. They can't release the right chemicals. And then they also can't do the job of absorption as well either, right? So more stuff stays in the GI tract. Um, and that leads to osmotic pressure. So that pulls water in with it, right? So cholera is the extreme case of this. Stool volumes up to 20 liters per day, right? So massive amounts of stool, massive amounts of fluid leaving the body, right? Again, we've only got about 6 liters of blood in our body, right? We have a lot more fluid in our cells and extracellular as well, but just to kind of put it into perspective, that's a lot of fluid, right? This is why cholera kills people, right? It's because it's just way too much fluid loss to sustain. And this is all about major reduction in sodium and chloride absorption, right? We talked before yesterday about how all the water reabsorption that occurs is sodium dependent, right? And so it's mostly about sodium being brought back and then water follows it, right? And so if we can't do that, that's what cholera inhibits is that sodium reabsorption. So we can't bring the water back either. Um, and so yeah, so then other intestinal infections, just like a typical stomach bug, right, is doing this same type of thing on a smaller scale, right, inflaming the intestines so we can't bring things in. Diarrhea results in hypokalemia due to potassium excretion in the colon. Okay, most of our potassium reabsorption occurs in the colon, and so this can be one of the kind of consequences of diarrhea. And then the main drugs that can be used for this are drugs that slow down intestinal motility. Okay, just kind of just make the chyme and make the food that we're eating sit in the intestines longer, so we have more of a chance to absorb things. That's kind of the primary method of the way that those drugs work. Constipation is just the other side of things, right? When there's not enough solutes in the lumen of the intestine and the stool gets dried up because not water doesn't get pulled in with it, right? And so then the common treatments would be things that create, or we put things into our GI tract that creates osmotic pressure, right? So magnesium sulfates are some of the real common ways to do that. So we don't absorb that, right? Increases osmotic pressure and pulls water in with it. So, and then obviously just adding more fiber to the diet to create that osmotic pressure and pull the water in. So, questions about those at all? Yeah, Brittany?
Might be off topic, but
Okay.
in terms of the differentiation between like magnesium sulfate and magnesium like glycinate, like does glycinate also play a role in like anything like GI related or
Where have you seen that? Where have you seen glycinate?
just from past experience?
Like in the hospital or?
No,
Hmm.
no, like in like
Okay. Yeah, I'm not super familiar with that. It's probably in the same group and probably has some of the same effects, I would guess. But I'm not totally sure. Yeah. Yeah. Yeah, Cheswa? Absolutely, yep, for sure, because it's something that our body can't break down, right? It can't digest it, so it stays in the lumen of the intestine and it acts as solute and increases osmotic pressure. Yeah. hmm Yep. Good question. Yeah. Other questions on that? Okay. Well, we're gonna kind of talk about each of the macronutrients next and how they're digested, how they're absorbed. But before we do that, let's kind of just look at an overall view of the whole GI tract and all the different processes of digestion, or all the different processes of the GI tract. And those include the list here, right? So we can see ingestion, right? That's obviously just getting food into our GI tract, starting up in the mouth, right? And then we go to digestion, right? So obviously ingestion is occurring in the mouth, right? Digestion, there's two primary kind of categories of digestion, mechanical and chemical, right? So the primary place mechanical digestion happens is in the mouth by chewing, right? By chewing and by the tongue smashing our food around, right? Where would be another place that mechanical digestion could happen a bit? The stomach, yeah, the stomach can move around a lot, does lots of churning. It's really showing this here, right? Showing that mechanical digestion. So yeah, lots of churning there. So the stomach, but then also the small intestine as well, as it says right here. We do segmentation, right? So segmentation is when we're kind of pushing the food along with peristalsis, and then the small intestine just pinches off in one spot and the food just hits up against that, right? The chyme hits up against that, which makes it kind of churn and move around, right? So there's some kind of mechanical digestion that happens with that segmentation that's occurring in the small, throughout the small intestine. Okay. And then chemical digestion is all, for the most part, driven by enzymes, right? But then also by the low pH of the stomach. Those are the two kind of primary ways that that happens. So mechanical, or not mechanical, but chemical digestion starts in the mouth with which macronutrient that we talked about yesterday? Carbohydrates only, really, right? We just have that salivary amylase. That's the only uh, enzyme that we're really including in the mouth and releasing with the saliva. But then we get to the stomach, um, and some of that chemical digestion continues with the salivary amylase that's not destroyed by the pH. But then we also have that low pH that's dropping, that's breaking up proteins. And then we also put pepsinogen, which gets turned into pepsin into the stomach, which is helping with protein digestion. So all of that's chemical digestion, right? But then we get to the small intestine, and then we get all of those different enzymes released from the pancreas. The bile is going to help with chemical digestion as well. So lots and lots of chemical digestion. That's really the primary way that we break things down, right, in the GI tract. And then absorption, for the vast majority of absorption happens in the small intestine, right, at least of all macronutrients. Okay, we get some vitamin and water absorption in the colon in the large intestine, but pretty much all macronutrient absorption happens in the small intestine. Okay, secretion would be when we're adding things to the small intestine or just to the GI tract, right? And so we talked about all of that last time, right? The nine or the 7 liters of fluid that are added to the small intestine, or sorry, to the GI tract. And some of that stays in, right? And that's a way that we excrete things too, right? Some of the cholesterol that we lose with the bile, but most of it comes back, right? Most of it is brought back. Okay. Propulsion is just moving things through, right? That starts all the way up in the esophagus, or really in the before we get to the esophagus, the pharynx, and then through the esophagus, and then all the way throughout. All right, we'll talk about that a lot more next week and all the reflexes involved in all those muscle contractions and how they work. And then obviously defecation is the final process to push it out. So questions about any of those kind of general processes? Yeah. Secretion, yeah. So secretion is when we're putting something into the GI tract that was formerly like in the body, right? Again, um, it's a form of adding things to a space that's continuous with the outside of the body. And so we'll use that same term when we talk about the urinary system too. So when the cells of the kidneys secrete something, that means we're putting it into the urinary tract, or at least into the tubes of the nephron. And so that's when we're taking something out of the body, putting it into that space that's continuous with the outside of the body. Yeah. Yeah. Other other questions on that? Yeah, go ahead. Um, say your question one more time. Uh-huh. It starts in the pharynx just a little bit, and it really starts with swallowing too, right? And so all of that's happening in the mouth and the pharynx, and then it's esophagus, stomach, small intestine, all the way throughout, really, through the whole tract. Mhm. Other questions? Okay. All right. Well, let's talk about each macronutrient here, and we'll talk about how they're digested and then how they're absorbed. Okay. So we'll start with carbohydrates. Okay. Carbohydrates, we're just talking about chemical digestion of carbohydrates starts in the mouth via that salivary amylase. Okay. And then it continues a little bit in the stomach via that same enzyme. There's not more of it that's released, and a lot of it is deactivated by the low pH of the stomach, but not all of it, right? There's still going to be some of it kind of mixed up in the chyme. Some of it's protected from the low pH because it's just kind of mixed up in there, right? So that process will continue a bit in the stomach. Okay. And then once we get to the small intestine, we have lots of different amylases released. Okay, so pancreatic amylases, um, and a lot of these are what are called oligosaccharide Okay, so we're taking long chains of polysaccharides, right, and breaking them down into smaller chains of polysaccharides. Okay, and so these are released in response to those hormones we were talking about last time, right? And so most of them are breaking down polysaccharides and hoping or getting us down for the most part down to disaccharides. Okay, so these will first kind of start breaking up those polysaccharides into shorter chains, but eventually getting all the way down to disaccharides. Okay, and then the disaccharides need to be broken down one step further before absorption can happen, which will be by brush border enzymes. And all these brush border enzymes are bound to the microvilli of the small intestine. That's what the background of the slides are, right? When we look at these um, villi first, we have the big kind of finger-like projections. Then on each of those finger-like projections are these little tiny hairs, microvilli, right? And so this is kind of looking at that. And then bound to the membranes of all these little hairs are millions and millions of enzymes, right? And these are the brush border enzymes, right? And so there's just many, many of these, many different types, right? And so yeah, we won't dive into the details of all of them. Obviously, there's lots and lots of them, but you can kind of look at the names of some of these, and it gives you an idea of what they do, right? So sucrase breaks down sucrose, right? Lactase breaks down lactose, right? And so yeah, so these are all breaking down those disaccharides into monosaccharides. And once we get down to monosaccharides, then we can absorb them. And that's really the goal, is to get it to monosaccharides before absorption can happen. Okay. All right. Then once we get it to get them to the monosaccharide form, we have a couple of different ways that we absorb monosaccharides. Okay, so two of the most common ones, glucose and galactose, are absorbed via co-transport with our favorite ion that we find everywhere, sodium. Right. So the sodium gradient strikes again. Right. We're using the sodium gradient again. Right. Always have that sodium gradient rushing into our cells because there's always a lot of it outside, not much inside, right? So there's energy in that, right? And so even when we have more glucose and galactose inside these intestinal cells, right? So this is like the lumen of the intestine where the chyme, where the food's coming through, right? We can see these microvilli coming off of those cells, and we can see that there's they don't show the digestive enzymes here, but they show the transport proteins instead here, right? So we can see that by the power of that gradient of sodium wanting to rush in, we can kind of slingshot or catapult the glucose and galactose into, even if there's more of it already on the inside, right? And that's so this is a form, again, of secondary active transport. Okay, and that can kind of vary, right? If there's not a lot of glucose in the cell and we just ate a bunch, and it's not necessarily secondary active transport at that point, right? If we're not going against the gradient. So it can just be kind of called co-transport. But even in the face of a higher concentration gradient on the inside, then it still keeps coming in, and that's when it becomes secondary active transport. So then the sodium and the glucose is in the intestinal cell now, right? And now we've got to get it out to the blood. Okay, and so we got to get it out to the blood, and that's done via GLUT2 transporters, right? We talked about GLUT4 is the one that comes to the surface when insulin binds to a cell, right? GLUT2 is the primary one that we're going to see here, that's going to allow that glucose to exit those intestinal cells, go through a little bit of interstitial space, and then get into the capillaries, so it's into the blood. Okay, turn to your neighbor real quick and see if you can answer this question. Why is the sodium potassium pump important here? Why is that important enough to add to that figure? Yeah. One. Yeah, I don't remember, to be honest. Yeah, I'm sure it's found somewhere, but it does glucose transport. I don't remember. There's like 7 of them. I don't know what they all do, but GLUT4 and GLUT2 are the main ones that we talk about. It may be in the kidneys. I'm not sure, but yeah, yeah. Okay, what do you guys think? What's so important about the sodium potassium pump here? Keeps the gradient 4. Yeah, absolutely. For the sodium to be lower inside than it is outside the cell, right? In order to keep this able to be happening, right? We need a sodium gradient to come in, right? If we just let that happen a bunch, then sodium's going to build up in here, right? So we need to get rid of it too. So we're pumping that sodium back out over here, right? So that maintains the sodium gradient. Yeah, and this little guy here is the sodium glucose transporter, SGLT1. This is just the name for this guy right here. And we find those in the kidneys as well, but just a slightly different form, the SLG2. Okay, all right, then so it leads the cell via GLUT2. Okay, there is a congenital defect where this mechanism is broken, and we can't get glucose and galactose into our intestinal cells. And it's absolutely life-threatening for sure, because there's glucose and galactose in most foods, right? And so this leads to a lot of osmotic pressure staying in the lumen of our intestines, right? And the only way to really deal with it is a zero glucose and galactose diet, which is not easy to make happen for sure. So I don't really know the details of that, like what types of foods wouldn't have those things, but it's very limited for sure, very limited diet. So pretty rare. Yeah, Kyle. I believe so. Yeah, I believe it's this. Yeah, this guy up here, the SLG. Yeah, GLT1. Yeah. Yeah, I don't think it's the sodium potassium pump. They'd be in big trouble if that was the case. But yeah, I believe it's the other one. Yeah. Yeah. Questions on that? Yeah, Ava? Yeah. It's a great question. Yeah. I think Andy and I were talking about this yesterday. Was that you that was? Yeah. Yeah. The deal is our body can make glucose, right? We can do gluconeogenesis. The liver can do that. And so it can take other carbohydrates or even fats and amino acids and turn that into glucose, right? So we can still have blood glucose. It's just the problem of putting it in our digestive tract. We can't get it into our blood from there, right? So yeah, so we can still have blood sugar, which would be glucose. But yeah, it's a great question. Yeah, other questions on that? Yeah, go ahead, Camille. This one right here. Yeah, the SGLT1. So yeah, think it stands for sodium glucose transporter is what that SGLT1. Yeah, and it kind of has a, this one is just like a general name, but it's talking about this one right here. Yeah. Yeah, good question. And then fructose is just another monosaccharide, right? And this is going to be entering in via facilitated diffusion with the GLUT5 transporter instead. And so we see that right here. Okay, and so this is just diffusing in with its gradient, right? Doesn't go in with sodium or anything via that GLUT5 transporter, and then still uses GLUT2 to get it out of the cell and back into the blood. So those are the only two that we'll look at in detail right here. And so then we can kind of see just a couple mechanisms here but with these two enzymes. So these are brush border enzymes, right? So sucrase, isomaltase, lactase, right? So the ACE means it's an enzyme, right? The OS will mean it's a sugar, right? And so sucrose is broken down there into glucose and fructose, right? So the purple one's the glucose, the orange one is the fructose, right? So that sucrase is going to break that down, right? The glucose goes in the mechanism we just talked about. Fructose goes in that other mechanism with GLUT5, right? And so that's just kind of showing the details of one example. Lactose is glucose and galactose, right? So that gets broken down by that lactase enzyme. And then both of those go in that same mechanism we were just talking about with sodium. So just showing a couple examples of what we were just talking about. So not necessarily adding anything there. Questions on that? Yeah.
E1.
Yeah, except for the fructose in sucrose. That goes through the GLUT5 mechanism. Yeah. Good. Other questions on that? Okay. All right. So that's it for carbohydrates. Let's talk about proteins next. Okay. So protein digestion begins in the stomach, right? So up in the stomach, we've got pepsinogen released, right? And then it gets converted into its active form, pepsin, because of the low pH. Okay. This is going to cleave some peptide bonds, right? So again, our long chain of amino acids, those are all held together via those covalent bonds, peptide bonds, right? That's the primary structure of a protein, right? That's going to be, some of those are going to get cleaved, okay? But by the time the chyme gets to the small intestine, the pepsin stops working because of the pH. Yeah, go ahead. I'm sure there is. Yeah, I don't know the exact number off the top of my head, but yeah, you could probably Google it. But yeah, the pH of the stomach kind of taps out at around 1, and that's kind of the one pH number that I know. But yeah, so. Yeah, and then the other thing that's happening here is obviously the protein's unfolding, right? And that gives access to some of those peptide bonds by these enzymes, right? Otherwise, it'd be kind of hidden in those globular proteins and things, right? So they kind of unfold. This gives more access to pepsin and the other enzymes as well. So then we get into the small intestine. And we have all of these different pancreatic proteases, right? So protease is just an enzyme that breaks down proteins. Okay, there's lots of different ones that are released in the pancreatic juice. Okay, and then we have lots of them, and so those are all shown here, right? And then we have some that are also brush border proteolytic enzymes. The key here in understanding this is, again, they're not sitting in those pancreatic cells in their active form, right? They need to be activated when they get into the small intestine. And this one here, enterokinase, it's not a pancreatic one, it's a brush border one. It's one that's bound to the membrane of the brush border. It activates one of the ones that's released from the pancreas, which is trypsinogen. Okay, trypsinogen gets turned into trypsin, and then trypsin is kind of the key to activating the rest of them. Okay, so we can see that here. Trypsin is going to activate chymotrypsinogen, turn into chymotrypsin, going to activate this one, this one. It activates all of these, right? So the activation of trypsin is real, or of trypsinogen into its active form. Trypsin is really kind of the key. that kicks off this whole cascade. And then now all the enzymes are active and they're working. Okay, so that started with the brush border enzyme enterokinase, right, which activated trypsinogen, which turned it into trypsin, throwing my pen, and then that activates all the other ones. So yeah. Okay, so now we're taking this down to mostly just kind of short peptide chains. There are a few single amino acids that are brought about here, but for the most part, we're just into like short amino acid chains. And then we're reliant on the rest of the brush border enzymes, which are called which are called aminopeptidases and others. Those are going to break down into dipeptides and tripeptides or into a single amino acids. Okay. This is just looking at two different kind of versions. And you guys might understand the protein nomenclature better than me, being in biochem, but these endopeptidases are acting on interior peptide bonds, right? And then exopeptidases are acting on the carboxyl ends. So yeah, that's just kind of a different groups of proteolytic enzymes there. Okay, so then how do we get these into our cells, right? So there's these 7 different mechanisms of getting amino acids in. You don't have to know them all, but just kind of a summary of it is 5 of those are the same way we just talked about with glucose and galactose via sodium cotransport. Okay, 2 of those 5 also require chloride, and then 2 are independent of sodium. Okay, so that's just like a little summary kind of that, right? There are some dipeptides, so meaning 2 amino acids together, and tripeptides, meaning 3 together, that can get brought into the cell without getting all the way broken down into single amino acids. And those are just some of the mechanisms over here. And a lot of these this one uses hydrogen ion cotransport. Okay, but then once these ones get inside the cell, then they get broken down into their individual amino acids before they get sent into the blood on the other side there. Okay, so that's just kind of a summary of that. So in general, we're still thinking about sodium cotransport for most amino acid absorption, right? There's a little differences there, but then a couple different ones can come in before they're broken all the way down into their individual amino acids. Okay, questions on that? Okay, and this is just kind of showing that process, free amino acids getting brought in via cotransport with sodium. Okay, so then the last macronutrient, digestion and absorption is lipids, and this is the one that has a few more steps to it. It's a little bit more complicated. I kind of have it laid out here in these 7 steps, okay? And we'll kind of talk through these 7 steps, and then I'll just have you guys kind of look through these pictures, kind of try to interpret what's going on with each of the steps here on these next few slides, okay? And so let's talk through it. So lipid digestion starts up in the mouth. Okay, we do, anytime we see lipase, lipase is the enzyme that's going to be breaking down fats for us. Okay, we have a little bit of salivary lipase. Okay, so there's not a major breakdown of fat in the mouth, but just a little bit. And then we also have gastric lipase release in the stomach. Okay, and so kind of we're just breaking up lipids just slightly. So again, taking big globules of lipids and just kind of breaking them up a little bit. Okay, so that's just in the mouth and the stomach, right? And then we get down into the small intestine. And like we talked about last time, bile acids are the key here in breaking up those big globules of fat into smaller globules of fat. And again, they surround them, separate them from the other globules of fat, and make smaller globules, right? And with that, we form those micelles, right? We looked at those last time where those bile salts surround them. Got the polar side on the outside towards the water, the non-polar side on the inside towards the fat, right? And so micelles kind of form this transport mechanism through the intestines, right? Because fats don't float well through a water-based medium, right? And so we need to kind of shuttle them over to the walls of the small intestine, and that's what the micelles do, okay? And then we're also releasing pancreatic lipases into the small intestines as well. right? And so this is taking us down into these smaller fat droplets that are just still carried in my cells, but broken down smaller when we get to this point. So then the micelles are dropping off these fatty acids and monoglycerides into our intestinal cells. Okay, so then we finally got out of the GI tract into the intestinal cells. And then inside the intestinal cells, these are then we add a little bit more of a carrier mechanism to these, and we surround the cells surround the fats with proteins, and this forms our first kind of what's called a lipoprotein, right? So proteins surrounding fats, and the name for this one is chylomicrons. Okay, so chylomicrons are structure that has a bunch of proteins around it, fats on the inside. So it's kind of like this protective way to be able to carry fat through a water-based medium, so it can still move well. Okay. Now here we don't drop off chylomicrons into the blood. They go in through the lymphatic system instead, right? So when we look at those villi that stick up in the small intestine, there's an artery, there's a vein, there's also a green one typically in the images too. The green one is the lymphatic system. These are called lacteals, right? And the lacteals are where the chylomicrons go into. The holes are just typically larger between the cells that line those the lacteals, and so we can fit bigger things through there, like the chylomicrons. And so then we got to get all the way through the lymphatic system to where that lymphatic system connects to one of our big veins, and then finally into the blood, and then through the venous system back to the liver, right? And so then the liver does the job of converting it into the cholesterols that we are used to seeing, right? LDL, HDL, VLDL is very low density lipoprotein, and then we go to even intermediate density lipoprotein, all these different sizes and densities of lipoproteins. Which one is the bad one if we're just looking at these two right here? LDL, bad. HDL, good, right? We want our HDL to be high, our LDL to be low. Looks like I wrote dad. There we go, dad. Okay. Um, okay. Yeah, so with that little kind of just intro, just go ahead and walk through with the people around you, kind of what's going on with these images, just kind of write it in probably in your own words. I think that's always a good way to study these types of things, is not just like write in the exact words here, but kind of describe it, what's happening using the right terminology. There's 3 slides to do that. Okay. So yeah, and then you can also, if you're done with that, you can start filling in this little summary of the absorption of each of the macronutrients. Okay. Go ahead, take a few minutes and do that. All right, begin here.
I'll just explain for this. Thank you.
All right. Okay, so we don't necessarily have to walk through this, but I'm happy to answer any questions that you have with this part. Any questions on this first slide here? Just kind of following those steps for the most part. Same thing here. The what I was kind of getting at with the why do fats go through the lymphatic system instead of the capillaries? A lot of it has to do with the size of those chylomicrons, right? They're a lot bigger than an amino acid or than a monosaccharide. And the gaps between the endothelial cells that make up the vessels of the lymphatic system are much bigger than the capillary gaps. And so yeah, a lot of it has to do with that. So yeah, we're seeing this apoprotein coat on the chylomicron. Yeah. If you've heard of apoprotein A, it's another kind of common cardiovascular risk factor. It's just it's a version of these chylomicrons that tends to be much increased risk of cardiovascular disease, much more. I don't necessarily know all the different types, but apoprotein A is something that they'll test for now somewhat commonly with a regular kind of blood panel, and puts you at a much higher risk for cardiovascular disease. Yeah, go ahead. Yeah.
where number 2 is on the last slide.
Uh-huh.
So is the emulsified lipids actually used in my cells? And then also in my cells, I guess it's in my cell on number 4.
Yeah, I think technically, they're maybe not called micelles completely until the fats have been broken down a little bit more into these free fatty acids and monoglycerides. Um, but this is kind of like the early micelle for sure. That's just kind of but I guess technically they're probably called just emulsified lipids at that point because they're still just kind of like globules. But then we need the lipases to actually take those globules and break them up into free fatty acids and monoglycerides. So I think the most technical version of the micelle would be we've got to get the fats into these forms first, and then they're still surrounded, they're surrounded the whole time, right? But the lipases are also working to break them up further while they're surrounded by the bile salts. That makes sense. Yeah, Andy.
Just the thing, lipase, it's not breaking bonds, it's just physically separating the free fatty acids.
It is breaking some bonds because we've got typically a lot of them are triglycerides, right? And so we're taking, so triglycerides will have the, kind of glycerol head and then the 3 fatty acids, right? So we're breaking those fatty acids off. And then, and then some of them are left just as monoglycerides, but then, so monoglycerides, the glycerol head with 1 tail, right? And then just free fatty acids with the glycerol part taken off completely, right?
Is that
So,
just, you have to break it down so they can actually cross through the membrane and then they're reformed into triglycerides just because that's a more efficient way of transporting this.
yeah, that's a good question. I'm not exactly sure how that piece works. Yeah, it's a good question. Yeah. Typically, triglycerides are, what we need to get them back to use them as fuel, right? And that's how they're stored in our fat cells as well. And a lipoprotein like LDL, VLDL is going to contain a bunch of triglycerides, is my understanding. So probably the liver probably maybe converts them back. I'm just not exactly sure on that part, but yeah, where that conversion happens. But yeah, good question. Other questions? Okay, I'll just point out here on this third one that it is important to know kind of the order of things here. So the chylomicron, right, is kind of our first step that's formed in the intestinal cells. But then that ends up in the blood, right? So we do have some chylomicrons in the blood, but then they do get broken down kind of to smaller chylomicrons or what they call chylomicron remnants before they even get to the liver. And then the liver is going to take that and break it into our VLDL first, which is kind of the biggest one, right? And then down to ILDL, which is just intermediate density lipoprotein, right? And then finally down to LDL, low density lipoprotein. And then the formation of HDL is a slightly different process by the liver, but these are kind of the steps to get it to LDL here. So yeah, in the order there. Okay. Yeah, go ahead, Joseph. Yeah.
Slide 10, we kind of went through that entire list of lipid digestion.
Uh-huh.
Step 6 says the
Slide 10? No, maybe not. Oh, maybe 20. Yeah. Page 10. Yeah.
So step 6 where it says step base system, how does it go from the base system to the lymphatic system and then to the capillaries? Like,
No, the lacteals are the lymphatic system. And so we go lymphatic system to venous system. I think you guys are working on this in the donors in anatomy lab where you see like the thoracic duct and a couple other places where the lymphatic vessels connect to the big veins up in the thorax. So that's what we're talking about is the connection of the lymphatic vessels to big veins. And now we're into the blood at that point, and it's going to stay in the blood at that point. Yeah. I was telling some of the other students, if you guys see those connections, I'd love to see it. I've only seen it in textbooks, but the lymphatic vessels are probably, they might be destroyed because they're really small and thin. So, okay, good. Other questions? Okay, so this here, I didn't write anything down for you guys to copy down, but we can talk it through. So the carbohydrates, which section of the GI tract digests and how, right? So we're starting in the mouth, right, with that salivary amylase, right? That salivary amylase continues to work some in the stomach, right? And then we get down to the small intestine where the rest of the digestion happens, right? Breaking it down into disaccharides by some of those pancreatic amylases, right? And then breaking down into monosaccharides, mostly by brush border enzymes there. And then we talked about those different absorption mechanisms, right? Sodium co-transport is the primary one, with fructose just kind of facilitated diffusion through the cell membrane. With proteins, we don't really do much to protein until we get to the stomach, right? And then the low pH denatures the protein, unfolds it a bit. All right, then we got pepsin to help start breaking up some of those long polypeptide chains into shorter polypeptide chains. All right, and then we get into the small intestine, and then we have all of those pancreatic proteases and the brush border enzymes and that whole kind of activation process we talked about with trypsin. So all of that is acting there. And then again, absorbing in the small intestine, right? All of these are absorbed in the small intestine. Most of the amino acids are absorbed with sodium. And then remember, there's a couple mechanisms where we can absorb dipeptides or tripeptides, and then those get converted into amino acids, individual amino acids in the cell themselves. And then we just went through this whole thing with the lipids. But any questions about any of those? Okay, so just a brief note on steatorrhea. Steatorrhea is defined as fatty, bulky, clay-colored stool. And it's formed by lack of fat digestion. And so this is typically caused with lipase deficiency. So typically some of those pancreatic lipases are not formed properly because of mutations in some of those cells. And so that's the primary cause. Sometimes the pancreas isn't secreting the alkaline secretions like it should be. And so if the pH is too low in the small intestine, then all those proteases don't work and we don't activate those proteases. And so then that's more on the stomach side. But this also can affect the lipases as well, or sorry, more on the protein side for the proteases, but the pH also affects the lipases as well. Can also be too much acid secretion in the stomach, so it's just too much for the pancreatic alkaline secretions to overcome when it gets down to the small intestine. And yeah, sometimes defective reabsorption of bile in the ileum. And yeah, and so other malabsorption disorders can include when there's a surgery, right? Surgery to remove part of the small intestines or part of the large intestine, right? And so if over 50% is removed, typically because of a cancer or something like that, or in severe cases of other autoimmune disorders like Crohn's disease, then yeah, it's termed short gut syndrome if over 50% is removed. Some nutrient impairment and nutrient absorption impairment occurs, but definitely vitamins as well. And then one of the ones that's had a lot more attention would be celiac disease. So celiac disease is, Andy, go ahead. Yeah.
You have to just supplement with more vitamins and nutrients then in order.
Most of the time.
My mom had
Mm,
cancer and she had most of her colon and small intestinal.
wow. Yeah. Yeah, so some vitamins need to be injected because they're not absorbed well in the intestines, and then others can be taken via supplements. But the absorption is the hard part, right? So a lot of times it is more of an injection that they have to do. But yeah, all depends on the severity. How does she do it? Does she do some kind of?
She doesn't get injected or anything.
Okay. Yeah. Just depends on the part of the intestine, and then that kind of dictates which vitamins aren't absorbed well. So yeah. Yeah, so celiac disease is autoimmune defense against gluten, which leads to inflammation, and then that inflammation eventually destroys the microvilli in the small intestines, and kind of can go towards this flattening, complete flattening of the microvilli, which then there's no space left for those all those brush border enzymes that are so important, right? The brush border enzymes are bound to all these spaces, right? So if all that surface area is gone, right, then lots is much harder to digest nutrients and then obviously absorb them as well. My son, when he was diagnosed with type 1 diabetes, they automatically check you for a bunch of other autoimmune disorders because you're so for example, with celiac disease, it's uh, it's 1% of the population that has celiac disease, but 10% of type 1 diabetics have celiac disease. So it's a tenfold increase in type 1 diabetics for celiac disease. So he came up with celiac disease. He had never had a single symptom in his life. It was pretty interesting. But we automatically had to put him on a gluten-free diet along with injections and finger pricks and everything when he was 10. So it was a rough transition for him, but he's got it figured out now. But yeah, so luckily for him, he never really had any damage to his intestines because they caught it so early. But for other people, the smallest amount of gluten can really wreck them. So yeah, yeah.
You find severity seems to like vary between how tolerant they are of gluten.
Mhm.
Is that just it?
Do they all have celiac disease or they do? Okay.
Also just their health.
Yeah, yeah, it does depend on when they caught it for sure. Like with Soren, my son, like if he gets a little bit of gluten, it's not really that big of a deal because he gets it so rarely, and he didn't have that initial damage. I think it didn't have that so much activation of his immune system. But it's also a lot of people are, kind of diagnose themselves with gluten sensitivity, which is a totally different thing, right? And it's not diagnosable by really at least accepted blood tests and things like that, like where celiac disease is, diagnosable. And so that's usually where the severity really varies a lot, is the gluten sensitivity versus celiac. But if they're diagnosed with celiac, then it's probably more just about probably when they caught it and how much damage they have to their intestines. Yeah. Other questions on that? Okay. Let's just do a quick review here. A lot of these things are from the pre-class video. So let's just do a quick review of this. And then I've just prepared like 8 questions that we'll do on Poll Everywhere to finish up. So work with your partner on this for a minute, and then we'll come back together here in a sec.
What are those?
Oh, wow.
Is that free? Yeah.
Yeah.
Mentioned, transparent in terms of, carrying.
Yeah.
Ferrous, but,
Yeah.
what?
That's what I'm looking for. Oh, okay. I see what you're saying. So there's a lot of iron in hemoglobin, but it's not in hemoglobin for the purpose of carrying it. All right. So this is just like getting iron, moving iron around the body via the transferrin protein.
Transparent is more for transportation.
Yep, exactly. Yeah. But yeah.
It was, like metabolized using transferrin.
I think yeah, what do you mean metabolized?
So you know how it goes from ferric to ferrous?
Mhm.
Does transferrin do that actually?
I don't think so. I think on the slide, the pre-class video slide, there was like an image that showed how it changed.
Yeah.
But is it, I think it has a different name for that. Yeah, it's some other,
Ferritin.
yeah, well, yeah. I think it's this guy, whatever that enzyme is. I don't know what the name of that enzyme is, but yeah.
Yeah.
Yeah. Cool. Yeah. Uh-huh. All right. Let's get Okay, so yeah, so I did write my answers in for this one. I know you guys will start writing and stop listening, but I don't know, I'll just put it up there anyways. But yeah, so what produces those short chain fatty acids? It's the bacteria in our colons, breaking down fiber, especially the soluble fiber, right? This is soluble fiber that gets broken down. And then the cells of our colon can actually use those nutrients for fuel, which kind of leads to some just healthy changes in the colon. And short chain fatty acids have been shown to reduce the risk of cardiovascular disease, diabetes, colon cancer, and just overall reductions in inflammation. All right, we got those two different forms of iron. In order to get it out of the GI tract into our intestinal cells, we got to turn it into the ferric form, which is the +2 form, right? But then to get it, once we get it back into our blood, we need it to be in the ferrous form, the +3 form. And that ferrous iron binds to transferrin protein, right? It's a nice name. It transfers ferrin, transfers ferrous, right? So yeah, so that's how we just carry it around through our blood. We definitely have a lot of iron in our hemoglobin, right? In our red blood cells, but it's there with a purpose, right? To bind to oxygen. This is when we're just moving iron through the body to get it to different places, uses that transferrin protein. And then intrinsic factor, B12 is what intrinsic factor helps with the absorption of. And then intrinsic factor, remember, was released by those parietal cells way up in the stomach, right? Which is kind of an interesting thing. It stays with the chyme all the way through, but then it's finally put to use down in the very end of the small intestine in the ileum, right? The last part of the small intestine, which is the longest part. Okay. Questions on any of those? All right. We'll try something just slightly different with our poll everywhere questions. They have an option to kind of make it like like the competition thing. What's the main one called? Yeah, Kahoot. But I don't think there's cool music and stuff like Kahoot, but we'll try it anyways. So maybe like partner up with the person next to you, or even however many people you want to partner up with. Just have like one phone that you're answering on. Okay. However you guys want to partner up is fine. Okay.
Yeah.
There's a QR code. One person per team join here. You can come up with a funny name for your team, a smush of your names maybe or something. I don't know.
Oh, yeah.
Yeah, I didn't really have an option on that. Just 1,000 points, a lot of points. Yeah. 1,000 points for the game, nothing to do with your score. Yeah. Yeah. All right. Huh? Raise your hand if you're still trying to get close. Coming up with your name still. It's important to get a good name. It's true. Okay. We ready? Yeah, guys are ready? Haley, ready? Okay. All right. Okay, here we go. Let's see how this works. We'll find out here. Okay. Which organ or part of the GI tract secretes the most fluid into the GI tract during the digestive process? Here we go. Remember, just like Kahoot, it does matter how fast you answer too. It does? Yeah. Like to get an idea of how many people are actually answering. So just raise your hand if you don't have your answer in yet. So we can, is everybody in? So is that our number? 17? Yes? Yeah? Okay, I'll give you a sec. Yeah. Okay. 18. Is that everybody in? Okay. All right. See how we did here. Okay. Said that. So what was it? It was like 2,500 mils, right? In the stomach? Yeah. 2.5 liters. Yeah. Okay. Um, all right. Here we go. 12 baddies. It's the cool group. I like this. Champagne and chill deal. Okay. I like it. Mr. Smith, this is good. This is fun. You guys are way more excited about this than doing it by yourself. I'm gonna have to do this next time. All right. Okay, ready? Here we go. All right, that's everybody. Here we go. Good. 8%. Perfect. Okay, there we go. Looking pretty good. Can we see the other ones? It's only showing we only see the top 10, I guess. All right, here we go. Here's another one. All right, I think that's everybody. Let's see how we did. Oh. Okay, about half of this is what leads to what's called the incretin response, right? Where we eat, and the presence of food in our digestive tract leads to insulin release. That's the main kind of grouping of these hormones. But then there's all the other things, hunger related and food intake, all those different things that the GLP-1s are acting on. So, okay, how we doing? All right. All right, got a little shifting around. The little lipids, I like that one. There's a little lipids. Yeah. Kahoot, okay. Comfy shred, okay. All right. All right, here we go. Here's another one. Okay. One more. Here we go. All right. I think that's everybody. All right. 61% of you saying gas. Let me just make sure this recording's happening right. Dang it, it's not. I knew that was gonna happen. I forgot to turn the video back on. Ah, sorry. Here we go. It's what is that? Where's my- There we go. All right. Sorry about that. Okay. Here we go. How are we doing? Oh, in my PJs took the lead. Okay. Okay. All right. Okay, here we go. Here's another one. So cell and what it releases. This is a lot. Yeah. All right, that's everybody. Let's see. Good job. Wow. That was a complicated one. You guys got it. 89%. All right. Yeah. Looking good. Looking good. Constipationers. I love that. All right. Constipationers. You guys made it on the top 10 list. Good job. Okay. Here we go. All right. Two parts to this one. Blank is used directly to drive the absorption of glucose and galactose into intestinal cells, whereas blank is used to drive these monosaccharides into the bloodstream. Semicolon is what separates the two. All right, that's everybody. Good. About 2/3 of you. Okay. All right. See how we're doing. Okay. Good. All right. Think we got a couple more here. Good. All right. Two more people, I think, two more groups. Anybody else? Somebody giving up? Yeah, oh, there it is. Good. Thank you. All right. Good. Most of you said trypsin. Good. Perfect. Trypsinogen will be the inactive form of that, right? Trypsin is the activated form. Yeah, Daniel?
Person able to like work it out in terms of plants.
Nope. But that's why I put directly. Yeah. Enterokinase has to activate trypsinogen to turn it into trypsin, but then trypsin's the one that directly does all the activations. But yeah, good question. Okay, all right. Okay. Megatron, that's a new one. I didn't see that one before. Frequent flyers. Yeah, that's a mysterious one in the back there. Okay. All right. I think I got one or two more. This might be the last one. Starting in the small intestine. Another one you got to read a bit. Everybody's there? All right. There we go. Good job. All right, our final score here. In my PJs. There you guys? Yeah? Nice. Kahoot, soluble sisters. I like that one. Who's the soluble sisters? Yeah, nice. Good job. Good job. Sorry, I need to bring candy next time. I feel like I need to reward you with something. Okay. All right. Fiber, yeah, high fiber candy for sure. Yeah. Okay. All right, guys, that's it. That's all we got. Have a great rest of your day. We'll see you next week. Okay.